Tuesday, okay, from 8 to 11, okay? So make sure you 8 p.m. to 11 p.m. It's online, so don't miss it. And we do have class on Tuesday. We do have class. It's just that there is a test online at night. It should not take more than an hour. I let it open so long, so in case some people have late classes or they have a job, so whatever. So don't miss it, because if you miss it, you will have to come to my office hours 8 a.m. next morning, in person, on paper. So make sure you don't miss it. Okay. So I have again updated those slides because magnetism is not that hard, but it's just it's heavy in concept. So the math is easy. You just have to make sure you understand the concept. Okay, yes.
We're gonna have lecture. Is the lecture gonna be the lecture stuff that we cover in class? Is that gonna be in the online test?
No.
Okay.
No, I will tell you what's gonna be on the. I think we stop. I forgot. So I will have to tell you on Thursday. Remind me. I forgot. No review. No. It's gonna be a lot of conceptual questions. Oh, I will. Oh, okay. So the test will finish. We're gonna finish that unit here. So the test will cover 3.1 and 3.2. Okay, now I remember. I will give you a hint today. And it's going to be also conceptual questions. So you need to know, you need to bring your right hand with you. So make sure you don't forget it. Here you have a cathode ray tube. You see, we talked about that. And using an electric field between the capacitor, you can deflect a beam of electrons. So an electric field accelerates, but you can also apply a magnetic field here because you have two coils. So you can have a uniform magnetic field here, and the magnetic field will deflect. So magnetic field can never accelerate. It will always deflect, okay? And that can happen only if you have a component of the velocity perpendicular to the velocity. Okay, so if a charge is moving parallel to the magnetic field, there is no magnetic force. If the charge is moving anti-parallel, there is no magnetic field. If the charge is not moving, there is no magnetic field. Okay, and if it's not a charge, there is no magnetic field, and I mean, like you have a neutron, and there is no electric field. An electric field can be experienced by a charge even though it's at rest. So it doesn't need to be moving. And even if it's moving parallel to the electric field or anti-parallel to the electric field, yes, it will accelerate. Okay, so for example, here you have a cathode ray tube. There is there is an electric field between the cathode and the anode. Here you have a little hole. So the electron will accelerate because the electric field is pulling on it. So remember, an electron wants to go against the electric field, so it's going to accelerate. And then it wants to keep going in a straight line at a constant speed. Now, if you apply a magnetic field, so here you have a permanent magnet, the beam of electron will be deflected. And that's when you have to play with your right hand. Okay, so we've seen all of that. Okay, so this is when it goes around here, like it's uh, what is it? I'm asking you. It's a cyclotron. Okay, remember the cyclotrons: accelerate, deflect, accelerate, deflect, accelerate, deflect. So at the end, you're going to have a very high speed proton, for example, that you can use for proton therapy, or you can use to make radioisotopes. Okay, so let's review. I just ran all the way there and then come back. So now my brain is like heating up too much. I don't know where I am. I'm here. Oh, cyclotron. Here we go. See, it very smart. It earned Ernest O. Lawrence a Nobel Prize in 1939. And if you've seen the movie Oppenheimer, he was working with Oppenheimer during the Manhattan Project, right? The building of the atomic bomb. And Ernest Lawrence built a calutron, it's called, to enrich uranium. Okay, so to sort out uranium-235 from uranium-238. So we talked about that. Okay, so about Ampere's law. So now I have made this new slide. Okay, so you keep track of all the equations. So this is a consequence of what we call Ampere's law. So if you have a straight wire, and of course it's connected to a power supply, so you have current flowing. Okay, so it's charge flowing. You're gonna produce a magnetic field that will circulate around. You see the magnetic field is going to be very strong close to the wire. So that will be that rule here with the right hand. And as you move away, it's going to decrease. So the magnetic field will be inversely proportional to the distance. And you want to use this equation. So make sure in your equation sheet and in the slides, at the end, I told you to print out, make sure that you recognize this equation. Make sure you know where to find it. So even though it's online, you want to make sure you don't want to take 3 hours, right? So you want to make sure to have all your equations ready. So you want to use this equation. Mu0 here is a constant. And that will be 4 pi times 10 to the negative 7. You can simplify, like last time I did simplify, and you have 2I over R. Okay, or you can keep it this way. Now, not to be confusing this equation with that one. Okay, so in that case, it's the second right-hand rule. So you have a loop of current. So maybe you have 1 loop, 2 loop, 3 loop, n loop. Okay, so it's going to create a magnetic field. We already talked about that. So you see your thumb here will be in the same direction as the magnetic field. So that will be the north face. That will be the south face. Remember that, right? It's like a bar magnet. This is the north and this is the south. So at the center, the magnetic field will be given by this equation here. So not to confuse with this one. Okay, that will be the lowercase r will be the distance from the straight wire. That capital R or uppercase R will be the radius of the loop. So again, most important before an exam, doesn't have to be a physics exam. You look at your equation sheet and you have to see through all the equations. You have to make sense of them. You have to understand what it means. And you need to know you need to have the right units. So, and then again, that was worked out by Amperes. His name was Marie-André Ampère, was French, Marie-André Ampère. And you see, if you have 2 wire, and I show you a demo, two wire carrying current. So if the current are moving in the same direction, the wire will attract each other. Okay, because this one is going to make a magnetic field that will be acting on that one. So you're going to have a magnetic force. Anyway, and if the current are going in opposite direction, they're going to repel. So if you have the same political view, you like each other, and if one is Trump and the other one is Biden, you hate each other. That's how you can remember. We have to laugh, right? Not losing our sense of humor. So that will be the force here per unit length. And you see, it depends on the current in the first wire, the current in the second wire, and the distance between them. Okay? So I try to summarize everything. Again, you need to have all those equations close to you for the final or for test 3. Okay, don't wait for the last moment. Oh, I was about to say bad word, but oh man, I forgot my equation sheet and you run to print it out. That will be too late. Okay, you need to have your equation sheet next to you and you have to make sure you understand it. Okay, so that's going to be on test number 3. It's a very simple equation that we're going to go through today. And you see you have your solenoid. Okay, you work with a solenoid in the lab, and you connect your solenoid to your power supply. Inside here, you're going to have a magnetic field that you can control with the current, right? So you increase the current, your magnetic field will be larger. And that's actually an MRI, okay? So if it's a huge solenoid, you shove someone inside, okay? So all those little nuclei will align with the magnetic field, nuclei being protons, proton belonging to hydrogen, hydrogen belonging to water molecule belonging to soft tissues. All those hydrogen gave up on their electrons. The electrons went to the oxygen, so that's why they are alone, spinning, and they behave like a small bar magnet. So anyway, so you have a magnetic field inside. That magnetic field is given by that equation here, and that's going to be the number of loops per unit length. Okay, we're going to see that today. But for example, if you have 100 loops and if the length here is 10 centimeter, so you will do 100 divided by 0.1 meter will be the density. Okay, so number of loops per second. You see something very surprising, and I will try to trick you for test number 3. You see this magnetic field, do you think it depends on the size? Does it depend on the radius r? No, there is no R. Here, when it's just a single loop, yes, it does. You see, you have an R here. So that means if you take a smaller loop, okay, B will be larger. But if you pack them together, and I do have a solenoid today for demo, those three. You see that it looks like this solenoid. It's also an electromagnet. So you see all those little wires here. It's really packed together, right? So when you have that, when you have a lot of uh, loops, so then it's not size dependent. Okay? So that will be one question on test 3. Ah, okay, so what else did I wanted to show you? This, yes. What did I say? So this, you see, the magnetic field inside the solenoid depends solely on the current flowing through it and the number of loops per length. Okay, loops per meter. How many loops per meter? Is that clear? Which is not the case if you have a single loop. Okay, so if it's not packed, so then you have to use that equation to find the magnetic field at the center. Is that clear? And to go back, because many of you are going to work in a research lab, so you see how a mass spectrometer works. We already talked about that. But first you have a bunch of isotopes, like neon. So neon has 3 isotopes. I pretend I know chemistry. I don't. I hate chemistry. But let's pretend I like it. So you have isotope 20, isotope 21, isotope 22. Okay? So let's say you have a bunch of isotopes, okay? But they all have the same number of protons, so they all have the same mass, okay? So you ionize them. So that means you strip off one electron. So all the isotope will get the same positive charge because they are all missing one electron. And then you're going to accelerate them through a voltage. Okay, so we're going to speed up. So then you apply the equation. So I don't know if it's on test 3 or not. Maybe, you know, potential energy Q times the voltage equals kinetic energy. Okay, so so here it has a high potential energy, electric potential energy. So it's like doing this potential energy, kinetic energy. So they're going to speed up. And then they go through what is called a velocity selector. Because even though they are supposed to have the same velocity, you learn in chemistry or biology that you always have a distribution. You know, the bell curve, right? So they have about the same velocity, but not, maybe some will go faster, some will go slower. So that's not right. You need to have one single velocity for all of them, all the isotopes. So the only thing that will differ will be actually will be the mass. Okay, so they don't have the same mass because they are isotopes. They have the same number of protons. So the only thing that differ will be the mass. Is that clear? I've said something wrong. All the isotopes have the same number of protons, the same number of electrons, but they don't have the same number of mass because some of them have more neutrons and some of them less neutrons. Okay? So for that, you use a velocity selector. So let me ask you something. Here you have an electric field, okay? It's like a parallel capacitor. So the electric force will be where? Up or down? See, it's a positive charge. You have an electric field between plus and minus. So a positive charge wants to go down. Very good. The electric force is down. Now you also apply a magnetic field into the screen. So let's review. You take your right hand. So from you, your velocity is going this way. The magnetic field is in the screen, so the magnetic force will be up. And we're going to tune the magnetic field that we can change with a coil, so with current, such as the magnetic field will be equals to the electric field. Okay, so that means that the force will be equal to each other. So you have QVB, so that will be the magnetic force, which is up, will be equals to QE, which is down. Can cross out the Q, and you see that the velocity now of all the isotope will be E over B. So that way I make sure that all the isotopes will have the same velocity. There is no more curve, what it called distribution. Okay, so this is called the velocity selector. So they all have the same velocity, all the isotopes. They all have the same charge. They go into the same magnetic field. They have the same velocity. So the only thing that will be different will be the mass. Okay, so the small mass will curve easily. The large mass is like a truck. It's going to make a large curve. You can have a detector that will move up and down, or this way, here in this direction. So you can find the mass of the isotope, or you can sort out the isotope, or you can count the isotopes. Isn't that cool? So many labs, you're going to have that. Okay, so let's go back to our Ampere's law. And here we did this one. So remember to be able to use your right hand. Okay? It's the same right hand, but different way to use it. So if you find the magnetic field produced by a straight wire, so you go like this. You see the wire is coming towards you, magnetic field like this, right? So the magnetic field produced by I1 is going to be up, okay? And that equation will be 2 times 10 to the negative 7 I1 over the distance here. Okay, now if you look at that magnetic field produced by the loop, then you do something like this, like that. The magnetic field is down, so you have B2 here. Okay, and for that equation, that will be 2 pi 10 to negative 7 I and the radius. And in that case, it just happened that R equals, okay? like this.
Why is it too late?
Because we just went for the big idea. This one. So if you have a wire, okay, wire, so current flowing this direction, the magnetic field will circle out. So if you have a wire coming towards you, okay, it's gonna go boom, 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 boom. Okay? It's hard to imagine. So you have to play really with your hand. You're lucky that today I don't have a back pain. Usually I always I'm doing acupuncture. It really works, right? If you have back pain. There is this place called Teva Wellness. I don't know if you know. It's but it works. Acupuncture works. And cupping works too. Well, that's a parenthesis. Uh, yeah, so you're right. It's not easy to see. It's not easy. Okay, this one is not easy. So that will be B uh, 1 from that one, and that will be B2. So you have to find their magnitude. And if you do the magnitude first, you see that B1 will be stronger than B2. So the equivalent one, the sum of the two will be up. So you have to subtract. Is that clear? Okay. So it's not that easy. So if you go back to here, so you can have all those equations ready. That will be the equation, okay, for B produced by a straight wire. That will be the equation for B at the center of a loop. R is the radius. Here, that lower case is the distance. So you use both equations. That's for B1 and that will be for B2. Is that clear? Okay, so don't confuse those. And by the way, I told you before, but I repeat things because make sure you don't forget. At the end of those units, 3.1, 3.2, you have the equations that I have found at the end of the chapter of your book, Johnson and Cutnell. So you want to print them out because I'm not sure you have all of them in your equation sheet. Plus, you have the explanations with it, which is very nice. Okay, you copy me? Okay. Yeah. Slide 88 and slide 16. Okay? You can bring it for the final as well. Okay, so again, if you have a loop, one loop of current attached or connected to a power supply, so you have current flowing, it will behave like a bar magnet. So that comes from your book as well. So that's why it's called a phantom bar magnet. So it doesn't mean there is a bar magnet here. It means that the loop of current will behave like a bar magnet. Everything happens like you have a bar magnet. Is that clear? Remember, magnetic field goes from the north, loop, it's looping around here, through the south, and back to the north. It likes to loop around. Is that clear? Consequently, if you have two loop, okay, so you do like this with your finger, that will be the north, that will be the south, and here you have another loop. Okay, so that will be the north and that will be the south. You see, they're going to attract each other. So it's like also if you have two straight wire and the currents are flowing in the same direction, they will attract each other. If they are flowing in opposite direction, because everything happens like it's a bar magnet, you see, you do this with your hand. That will be the north, that will be the south. Here, that will be the south, that will be the north. They will repel each other. Okay, so two loop of current will interact with each other. Is that clear? So that's why when you pass by horrible, like next to a Sunny Eyes bridge, you see you have all kinds of transformer and you hear like this. This is because all those wires, they vibrate constantly because they push and pull on each other and it makes this humming noise, right? Plus it's ugly. The issue here is you cannot have things in the ground. You cannot hide anything in the ground because there is no ground. It's just water. So if you have a solenoid here, so now it's packed. Okay, so all the wires are really packed together. Okay, so in that case, you're going to use these equations. You have three equations so far. Inside here, the magnetic field will be uniform. Okay, so again, you take your right hand, you go around like this, your thumb, the thumb will show you the north. So that will be the north, that will be the south. So it's behaving like a bar magnet. If you shove inside soft iron, a piece of iron, it will make the magnet even stronger. Okay, so let's try to do this. You have two layers. So if you have two layers and each layer is 40 turns, so that means you have 80 turns together. Is that clear? Okay, so you can do it. I have my notes all over the place. Did you notice that they decreased the AC? Right? It's now I think it's too hot. So mu zero is 4 pi times 10 to the negative 7. The total number of loops is 80, okay, because you have 40 turns or 40 loops, but you have two layers, okay? N is the density, so N by definition is the number of loop per unit meter. So that will be 80 divided by the length here is 0.5. So it's a density because the unit will be loop per meter. It's a density. I'm sure all of you take chemistry. You have a lot of density. You work a lot with density, right? So B equals 4 pi times 10 to the negative 7. I forgot the pi. 4 pi times 10 to negative 7 times n, so 80, okay, divided by 0.15 times the current, so 0.3. So B equals what? Yeah, did you get that? 2 times 10 to the negative 4? Huh? So 4 pi, don't forget the pi. 4 pi times 10 to the negative 7 times, enter, times 80 divided by 0.15, enter, times 0.3. Did you get that? Yes, you sure? Okay, so 10 to the negative 4 is 1 Gauss. So B will be equals to 2 Gauss. And you see, it does not depend on the size here. Doesn't depend on the size. Okay, and so here you have the set of equations. So you're gonna use this one. So that will be the magnetic field produced by a straight wire. That will be a magnetic field produced by one loop, two loop, or three loop. But if you have a solenoid, so that means a lot of loops, like 1000 loops, for example, you're going to use this equation. Okay, this one you don't have to worry about it, or you can read. It's Ampere's law. Ampere's law says that magnetic field wants to curl around current or moving charge. That's what magnetic field do. Ampere's law. Okay, so now we are at electromagnetic induction. So remember that in 1820, you have Oersted, who did that experiment, and he was able to show that the source for magnetic field is moving charges, right? So if you have an electric current, it's going to produce a magnetic field. So that was 19th century, 1820. And then the next question is, if electricity can generate magnetism, then will it be possible that very good, magnetism generate electricity? But how? Okay, and that's how we have electricity today. And it took like 10 years to figure it out. And that was found, the answer was answered by Michael Faraday. Very interesting character because it was the 19th century England, so it was not cool for kids at the time. I don't know if you read the books by Charles Dickens. Okay, they use kids to work, right? So many of them would die if they were not very wealthy, and they would not go to school past 12 years old. Okay, when you are 12, okay, you go to work. So many of them had to work in mines or doing very dangerous jobs. So it was not very nice for the kids at the time. If you were from a wealthy family, you will get tutors. Okay, otherwise that's it. 12 years old, okay, you go to work. And he was very lucky. He was the son of a blacksmith of very poor family, and he went to work in a bookstore. And the time the book, the where they will put the book together, you had to sew them. Have you seen those very old book, right? With us, so that was his job. So he because he was working in a bookstore, he educated himself, and he became very passionate by science, chemistry, and physics, right? And so he was self-educated. He didn't go to school past 12, and he didn't go to college, and of course he didn't go to university, but at the end he is the one who figured out how to produce electricity using magnetism just by doing experiments, right? He got a job at the Royal Institution of London, and he was just a lab technician. He was helping, I don't know if you remember this guy, Humphrey Davy. Do you remember the guy who would get high with the laughing gas, right? He damaged his lungs so much that he died. But he was a chemist. Remember, he used electrolyte to discover so many compounds. And he was very good at giving public lectures. Of course, he was getting high before, so we can understand why. So anyway, he became his lab aide, okay, technician, and he actually surpassed his mentor, okay. And Humphrey Davy was really upset at him because he did that amazing discovery how to make electricity using magnetism. But Humphrey died, from lungs issues, and he became in charge of the Royal Institution, and he was very into giving public lectures to educate everyone. So that was Michael Faraday. It's a very interesting story. He was not good at math, of course, because he didn't have the proper education, but he was very good at doing experiments. And the next scientist coming was James Maxwell. Okay, so he looked at everything Faraday did and others like Ampere, and he put everything into equations. So James Maxwell. So anyway, so what did he find? He found the way to produce electricity using magnetism. So here you have a nice, so this comes from a book. a very interesting book by Paul Hewitt. Another interesting story about Paul Hewitt. Okay, he was in high school and his teacher said, "Okay, don't go to college. You are not gifted enough. You are just good at art. You go do drawing. You can have a job by drawing." And but Paul Hewitt, he did that for a while and he came back to college and he became this very famous professor. Okay, so you have to stand by your passion, ideas. Also interesting story. So anyway, he wrote a book, Conceptual Physics, and he's very good at drawing, except he used his skill for that physics book here. And you see, how do we produce electricity? Look at that. So you have a horseshoe magnet. So you can have a magnetic field, right? From the north to the south. The magnetic field is actually uniform. And here you have a conductor. Okay, that conductor here makes a loop. Okay, so it means it makes a circuit, but there is no power supply. Do you see any power supply? There is no power supply. Okay, but you're gonna move that conductor. Okay, you're gonna spin that conductor inside the magnetic field. So that means the magnetic field lines here are going to go through this area. Okay, so there will be a change. So you are moving the conductor. We're going to see that in detail, but we're going to move the conductor relative to magnetic field. And that's when you're going to produce electricity. But what kind of electricity do we produce? Is it DC or AC? AC. Okay, so it means even the light that you see here, it's flickering, but it's flickering so fast that your eyes does not have time to to get the change, right? Because it goes on and off 60 times per second. And that's how we produce electricity. So somewhere we have a power plant. You need to burn some fuel, like maybe fossil fuel or nukes, and you're going to move a conductor inside the magnetic field. You have those wire, high tension wire, and here you're going to have your house. Okay, so that's called electromagnetic induction, or Faraday's law of induction. Okay, so I'm gonna show you some demo. But here, interesting. So 1921 was the Oersted experiment, even 1920, I think. So it took 10 years to figure this out. And it's Faraday, who didn't go to college, didn't go to school, who figured this out. So I think it's a really beautiful story. So what you see here, that's his notebook, and you can see the right hand rule, right? You see the loop here? It's going counterclockwise. The thumb, so the thumb is towards you, the thumb, but this one is towards you, so that will be the north. If it's going around in the opposite direction, so you're going to see the south. Okay, and that's also, oh, let's talk about that because that's going to be also on the test number 3. I just added it. So he built the first motor. Okay, so motor, of course, you have a power supply. So you have electricity here. Look, what is it doing? You have electricity flowing this way, that way, and here you have a liquid. What kind of liquid is a conductor? So, it could be water and salt, but in that case, it's a special kind of metal with a high density that you use in a thermometer that we mercury, right? Back then in France we had them. Here I don't think you have them anymore. But mercury. So mercury is a conductor, it's a metal. So we used mercury here. So the current is flowing in this direction, that direction, and then it's going back here, and then it's making a loop here, and then it go back to the power supply. Do you see that? Now remember, let's figure out why is it spinning in this direction. You see, you have a bar magnet here, right? You all agree? So the magnetic field will go from the north into the south. So it will be in this direction here. Okay, make a loop here from the north into the south. and you have the current here flowing in this direction, right? So what's gonna happen? You have the current flowing this way, okay? This way, the current is flowing, that current here, that current is flowing this way, right? Going this way, magnetic field is up, so the force will be into the board, right? You see that? The current is flowing this way, magnetic field is up, the force will be into the board. So it will apply a torque to the wire. Okay, so I'm too warm here. Aren't you hot? No, it's too hot. I don't know what they did. Some people complain too much here, so no. So the magnetic field go this way, you see, up to the north, from the north into the south. So that will be the magnetic field B. That will be the current. So the force will be into the board, into the screen. So the current magnetic field is up, the force will be into the screen. So it's going to start to rotate, okay? It's going to rotate about the axis. So you have a motor. It's like the first motor that was built by Faraday. Is that clear? Okay. So you have current flowing in this direction, magnetic field is flowing in that direction, so is a torque into the board. Maybe it's like challenging, I don't know. I might remove that question. Okay, so so then 10 years after the experiment done by Oersted, he found how to produce electricity. So here is the principle. You need a magnetic field. Magnetic field, you can get it with a permanent magnet or with an electromagnet. Second, you need a conductor, okay? So electricity can flow through. Third, something has to move. Either you change the magnetic field, okay, or you move the conductor. So here you have three ways to do it. You have a conductor here, so it's a loop. You bring a magnet, okay, toward the conductor, so you're gonna increase the number of lines poking through this area. So you can imagine here you have like a soap film here, like a film attached to it. It's imaginary. So if you bring the magnet toward the conductor, the number of lines poking through this area is going to increase. As you move away, you're going to decrease the number of lines. So the secret is that the number of field lines poking through this area has to change with time. If you do that, you're going to induce a current, you're going to induce a voltage, and we call that voltage the EMF. Okay, I'm going to show you a demo so you will understand better. So that's one way. Or different way to do it, like if you have a conductor here, okay, it's a loop, you have this area like that film attached to it, even though it's imaginary. So you have the magnetic field poking through this area. If you decrease the area, what's going to happen to the number of magnetic field lines poking through? It's going to decrease, right? So because there is a change, you're going to induce a current flowing through it. Or this is the way we do it. You spin the conductor inside the magnetic field. You see, you spin it. And so the number of lines will change with time, and you will get an induced voltage, induced current. Okay, so I will show you some demo. I understand they want to conserve energy but here it's very hot. I'm not teaching this summer, okay? Now this one is not. I have another one which is better. Um, okay, so how do we produce electricity? Come on. Okay. Okay, so what is that? That will be the conductor. Do you agree? You see, it makes like a circuit, and here you have a load. There is no power supply, and there is no electricity flowing. That's going to be the electrons, right? So electrons are not moving, so there is no electricity produced. That's going to be your magnetic field. And can I show the magnetic field? Okay, so the magnetic field here is poking through this area here, but the number of magnetic field lines, okay, going through here, poking through is not changing in time. So here what I'm going to do, now you see, the magnetic field is going to change with time, and here I'm going to induce a current. So this is called electromagnetic induction. Okay, and you are also inducing a voltage, but that voltage will be, what type of voltage do we induce? AC. So if you have a power plant, that part here will be called the rotor, so something has to spin. This one is called the stator, okay, stator, because it's not moving, and then that will be connected to your house. So that's how we get electricity. So something has to move. You need a conductor, you need a magnetic field, so you need a magnet or an electromagnet, and something has to change with time. So what's happening here is the magnetic field lines poking through this area that will change with time. So this is called the law of induction. But when this happens, you can only get AC. So there was a big fight between Tesla and Thomas Edison. Thomas Edison wanted to have DC everywhere. Tesla wanted to have AC. So Thomas Edison was very wealthy. Tesla was penniless. But at the end, Tesla won, but he was already dead. So what's going to happen if I make it spin faster? What do you think is going to happen? Okay, I'm going to induce more voltage, the EMF. Does it make sense? Guess what? The time it takes to go around, okay, it's the time for one cycle. That will be the period. The number of cycles per second is called the frequency. Guess what's going to be the frequency here for the power plant that we have? Remember, from the AC, 60 hertz. Okay, that's what that 60 hertz comes from. Remember, the electricity that we get from the outlet is going back and forth. It's a sine, up and down, up and down, up and down. So the hot holes that you have here, the connections go plus minus, plus minus, plus minus 60 times a second. It comes from there. Okay, something is spinning 60 times per second. That's why you have 60 hertz. So the voltage that you get here from the outlet, that's from the outlet. It's going to go back and forth 60 times per second. And we managed to have here 120 volt. Okay, so that's how electricity is produced. If you make it spin slower, okay, if you make it spin slower, the voltage induced, so which is called the EMF, it will be smaller. Is that clear? If you increase the area, look, if you increase the area, you can also produce more voltage. So it's area dependent here. Okay, I can make the field stronger. Okay, so let's go to demo. I think that will be the last demo I do. It's a lot. So a lot of things to carry. Okay, so remember why did we use this one? Huh? Do you remember that demo? It's called a mo. No. Something that spin when you connect to a power supply. Motor, right? It's a motor. Ah, I brought one. I will show you after. So it's a motor. You connect that to a power supply. Okay. Do you remember the loop once? So electricity will flow. The loop becomes like a bar magnet. So south wants to face north. Okay. But because it's losing connection, it will keep turning. But you can use also this to produce electricity. So how does that work? That will be your conductor. Okay, that will be your magnetic field. Okay, so which one is changing? It's not the magnetic field in that case. It's the conductor that will spin. So imagine now the magnetic field coming from the north, going this way. So it's like a wind blowing. Okay? It's like a flow. You have a flow. Okay, that flow is going to go through that loop. But if the flow does not change, nothing will happen. If I put my loop like this, is there any magnetic field going through the loop? No. Okay, here it will be maximum. Okay, so magnetic field here is like a flow going from here through it. If I do this, the flow equals 0. So if you want to induce current here, or EMF, the flow has to change. So that's why you need to rotate. Got that? So let's see if it works. I'm going to connect that to a voltmeter. Yeah. Tell me if you see, because I cannot do two things at the same time. You cannot see, cannot look up and look down, because I have only two eyes. Okay. Can you see here? There is nothing special, right? Even if it's like this, almost nothing. If it's like this, almost nothing. Now look what's going to happen if I'm going to spin. Ready? Are you ready? Ooh! Do you see that? I am inducing a voltage. This is called the induced EMF. You see? It depends on the speed. Okay, if I go very fast, I'm going to induce maybe 15 millivolts. Right? If I go very slow, you're not going to have much millivolt. So that's how we induce current. So it's very cheap to make electricity. When you are paying your electric bill, you are just paying the membership actually, okay? Because otherwise, fossil fuel is very cheap. This is very cheap to make, so electricity is very cheap, supposedly, except if you live in Hawaii. So if now I am measuring the current, okay, I don't know if you can see, is there any current here? No, there is no current, right? If you have a spin, do you see? A few milliamps. Oh, one. Do you see the one? One milliamp. Okay? So this is how we induce electricity. So you have to imagine a flow here. Okay? That flow is going through this area attached to that. And if the flow is changing with time, that's when we're going to have an induced current and induced EMF. And this is all thanks to the son of a blacksmith who didn't go to college and barely went to school. So amazing. Okay? And was very determined because it was not easy. He was very stubborn. Okay, so this is what I used to do with students. Okay, I had them read this. So you see here inside, I don't know if you can see, you have a magnet, a neodymium magnet. Can you all see that? Around there, you're gonna have a coil all around. You see, I did that. Okay, so what's gonna happen? You see this area? Okay, that will be the area, attached to the conductor. So the magnetic field line, when it's gonna spin, it's gonna go and change with time. So let's see if I can induce. Okay, I'm gonna take a different voltmeter. I'm gonna take this one. So what do you expect? Is it going to be a DC voltage or an AC voltage? AC, very good. AC voltage. Okay, so the magnetic field lines produced by the magnet pop through this area, but the number of lines will change with time. If my magnet is this way, there is no field lines. If it's like this, there's a maximum field lines. And because it's going to change with time, I should be able to produce, but it's hard to spin, but I'm going to try. Can you see the volts here? Let's see. You see that? And you see it's moving to the left, to the right, to the left, to the right, to the left, to the right. So it's AC. If I go really, 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 really fast, it's very, very, very hard. I'm going to increase the EMF. Okay? So somewhere in the power plant, okay, electric power plant, you're going to have a coil, okay? That will be called the stator. That will be the rotor, except instead of using permanent magnet, we use electromagnet, and it's going to spin inside, okay? So we're going to produce electricity. You're going to increase the voltage to 100,000 volts, okay? Electricity will flow to your house. There, electricity will step down to about 20,000 volts, and then furthermore to 120 volts, because we don't want 100,000 volts in our house. I don't think it's a good idea. And then you have a LED. So I have a LED here. Let's see if I can make it shine. So LED is polarized, so it will. It's okay, it should still work. No, where to put it? Maybe I do it. Okay, can you see the LED here? Oh,
Oh, there you go.
you see that? You see? You see the flash? Okay, so that's how we produce electricity. This is your house. This is the high tension line. This is the power plant. And this here is spinning. Okay, it's spinning at a rate of 60 times per second. So your light here will go on and off 60 times per second, except you cannot see it with your eyes, right? You can see it with a phone, with a smartphone. You can take a video of the lightning. Ah, yes, you have to slow it down. Okay, it could be a demo to do for extra credit. I don't know how to do it, but you are young, more high tech. You can do that. Okay, let me show you another demo. But it's always the same idea. I'm lost with all of them. Okay. So those type of device are called crank generator. And if you go to camping, okay, you don't want to take battery with you. Instead, you can buy on Amazon what is called a crank generator. So you crank, okay, you charge the battery and the light will go on for a long time, or the radio, or you can send an SOS, for example. So you can produce electricity with a crank generator. You can buy it. You can buy it online. Um, except my crank generator doesn't work. No, it doesn't want to work. Well, if it doesn't work, it's okay. Oh yeah, I see. Can you see? Can you see it? You see it? Okay. Um, I had another crank generator. Which was very cool, except I don't find it. What is? I thought. I think I hope I didn't lost it. Oh no 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 no. Ah. And that's good also for understanding chemistry. So application in modern physics. Remember how electrons are on the electric energy level, right? So for example, here you still have a crank generator. So you see you're going to have the magnet, but the magnet is like a donut, and you have two coils. So again, you need a magnet or an electromagnet, and you need conductors. Okay, so here I have two coils, so two conductors, and something has to move. So something has to change with time. And here I have LED. And what you're going to see here, if I go slow, very slow, I'm going to lit the infrared LED so that you can see only with your phone. If I don't put too much energy, you can lit which LED? I don't know if you can see here. Which LED is that? Which color is it? Red. And if I go faster, red, green, and then blue. Because blue, it takes more energy for the electron to make to a higher level of energy, right? So you need to input more energy. Red does not need a lot of energy. So I can do it slow, and then I increase, and then you get blue. Isn't that beautiful? So you can buy that online, okay? So if you go camping, uh, you can have those in case of emergency. A crank generator. Crank generator. Extra credit, you can make one. So, crank generator. Okay, and the last demo, and then we stop. We stop with the demo. I forgot. I have to cheat here. So if I connect that to my voltmeter here, it's a solenoid, exactly. You see, it's a solenoid. It's a solenoid, so I can use that as a conductor. Okay. So interestingly, thank you for noticing that it's a solenoid, and you're gonna see that more loops you have, stronger is the EMF. Okay. So as you increase the number of loops, you're gonna increase the induced voltage. So you're gonna increase the current. So the EMF will depend on the number of loops. It will depend on the area. as well. And it will depend how fast the change happens, how fast the magnetic field, the number of magnetic field lines poking through this area is going to change with time. So you can imagine here, you're going to attach here an area, okay? I'm going to take a magnet in and out. So the number of lines going through is going to change with time. Faster, more EMF. So let's see if it works. I'm going to attach that to a voltmeter. Okay, so we have a closed path. Okay, so it's a circuit that goes loop, 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 loop. And here you have your voltmeter, but the loop is closed. So you have a conductor. And now I need a magnetic field. So I'm going to use a magnet. You know, I am the only one to do all those demos. It's very hard, especially it's very embarrassing if it doesn't work. So I'm going to take a bar magnet. Okay, I'm going to amplify the magnetic field with a neodymium magnet. And if everything goes well, you see, I'm producing like really, really fast. It's very hard. But you see that I'm producing EMF, right? So you have a magnetic field here coming out. Okay, so it's like field lines poking through this area. And if the number of lines is changing with time, I'm going to have an EMF. Instead of using this magnet, instead I can use an electromagnet, exactly, but I don't know where I put it. Do you remember I showed it to you before? Okay, if I don't find it, it's okay. You see why you don't want to do a demo? It's a mess now. You remember I showed it to you, right? The small one?
I think it's on the floor.
Ah, it's on the floor. Oh, yes, thank you. So I can take a, and remember, this is an electromagnet with a soft iron inside. Okay. What do I need so it becomes a magnet? I need a, huh? I need to connect it to a power supply, right? So then it becomes a magnet. I'm going to connect that to a power supply. Okay. Okay, so now I have a electromagnet, and if I do this in and out, ooh, it's even better. Do you see? Ah, it's getting tiring, but you get the idea, right? Okay. So if you get inspired, if you want to do some so many demo that you can do for extra credit, it's even better than last semester, right? Okay, I'm done with the demo. Okay. Oh, you have this one also. You see, I have loops here, so it's a conductor. You have here the field lines. You see? So we review for the test number 3, feed lines going out of the north into the south. Do you agree? Okay. Do you see something special here? Is there electricity flowing? No. Right? The magnetic field lines are poking through this area. So the area that you attach here to the coil. Now what you need to do is something like this, right? You have to move so that you increase the number of line to decrease the number of line. You increase the number of line, you decrease the number of line. And then you get AC. You see how it works? If you attach a voltmeter instead, you see how you produce AC. Okay? Now you can change the number of loops. Less loop, less voltage, more loops, more voltage. Okay, so if you have, so it's called Faraday's law of induction, and have a small GIF somewhere, but I don't know where. Uh, Maybe this one, I don't know where it comes from. So you can see here, so in that case, you are not moving the conductor, you're the electromagnet, you are not moving the conductor, but you see you turn on and off the magnetic field because you turn on and off electricity. So magnetic field line will increase and then it will decrease. That's enough to induce current. But I had a nice GIF. Okay, let's see. I have a demo here. Oh, this one. This is my favorite one. That's my favorite simulation. Okay. You see how it works? Okay, you are inducing current. There was a short movie also that I have here. Purdue.
In 1831, Michael Faraday in London and Joseph Henry in New York independently discovered electromagnetic induction. I am going to demonstrate electromagnetic induction with an experiment similar to the one that Michael Faraday performed. So I have an ammeter here, a magnet, and two coils. This coil has 100 turns, and this coil has 25 turns. I will first connect the 100 turn coil to the ammeter. I am now going to take the magnet, and notice as I move it towards the coil, I get a pulse of current in the positive direction, and when I pull it out, there's a pulse in the minus direction. And notice if I just hold the magnet there, there's no current flow. It's only when the magnet's moving and when there's therefore a change in magnetic flux with respect to time inside the coil. If I move the magnet...
So what it's called the flux is the number of lines poking through this area. Okay, you have an imaginary area, you have lines poking through. That number of lines change with time. That's when you have
slowly I get a small current, and if I move it quickly I get a larger current. Okay, so it's the rate of change of magnetic flux inside the coil that determines how much current is flowing. And we see that I can get about 10 microamps if I try to move the magnet very quickly. Okay, so now let me connect the 25 turn coil. So I have 1/4 the number of turns. And so again, if I move the magnet and try to move it as fast as I can, you can see from the deflection I'm only getting about 1/4 of the current flow. Let's summarize what we have observed. Okay, so we saw that...
Okay. Okay, so again, if you want to induce a voltage called the EMF, you need to change the number of field lines poking through this area. So something has to change, okay? So you could change the area. So for example, here, look, there is no power supply. This is just, let's say, like loops of current, loops of wire, sorry, there is no current, okay, nothing is happening here, it's just a loop of current, like a coil. If you change the area, then you're going to induce electricity. Isn't that interesting? If you have a magnetic field here, okay, and you have a loop here, okay, so it's just a loop of wire and loops of wires going inside this area with a magnetic field. The number of magnetic field lines poking through this area here will increase with time. That's when you have an EMF, okay? Don't fall asleep. We almost getting to the math, okay? Stay with me. Bear with me. I see people like going like this. Okay, don't sleep. So this is the experiment I was trying to do, but that was back then, okay, at the Michael Faraday time, so mid 19th century. So you have a battery here connected to a solenoid, okay, so that will become like a bar magnet, and you go in and out, you're gonna produce a voltage, or you're gonna produce EMF, or you're gonna induce current. Okay, so that was done back then. Okay, so we'll talk about that next time, because I want to get to the math. And then we'll go back next time because I know it's going to be a lot. So you're going to induce. So doing this experiment like the guy just did, okay? He moves a magnet in and out. You're going to have a current flowing through the conductor. If a current flow, that means you have a EMF. That means you are inducing an electric field that is pulling on the charge, making them flow. So you're going to have an induced current and induced voltage. The term of EMF was introduced by Michael Faraday himself. So because it was the great Michael Faraday, we didn't change it. We don't say induced voltage, we say induced EMF. That's just a vocabulary. Okay, so how can we find the induced EMF? So here is the equation. Okay, so the induced EMF will be equals to the number of loops, okay, times the change in flux. So you can use this equation here. So we're going to see that the magnetic flux is going to be the magnetic field times the area. So the EMF induced, you can use this equation here. So magnetic field times area times the number of loops, that's what we call the magnetic flux. It's a way to compute the number of magnetic field lines. Okay, so let's do the math and then it will seem easier. Okay, let me show you the math first. So the EMF, so the voltage induced, equals the number of loops in your conductors, right? Because you have wires, you have a wire going around and around and around, times, that means the change of flux, and flux is magnetic field times the area. Okay, so that will be the equation that you're going to use. So something has to change. In that case, we suppose that B is perpendicular to the area, okay? So that means if you have an area here, okay, that will be your conductor. Okay, we can say that B is always perpendicular to the area. So we can use this equation here. So A will be the area of your loop. That will be your magnetic field. So that will be in Tesla, that will be in meters square, and that will be in time. So that means the EMF will be equals to the change means after, so B after, area after, minus B before, area before. And here you're going to put the time elapsed. Okay? So let's find how to use this equation here. The first thing you need to ask is what is it that is changing? And that comes from your book again, Johnson and Cutnell. No, I want to move. Okay. So a coil of wire. Okay, so that means you have a coil of wire. So let me make the coil. So this is my coil of wire. So that will be my imaginary area, A. Okay, that will be N, the number of turns, yes? Yes? This is like my solenoid. This is this, like this. You see? I have a coil. Oh my God, what is that? Someone is moving something. So this is my coil. Do you see the coil here? It has 20 turns, and this is the area. You see, pi r squared. That will be the area, okay? So you have the area A. So this is the area A here. So the area A equals 0.0015 meters squared. And then you have a magnetic field poking through. So maybe you have a magnet here. That will be north, that will be south. And you have magnetic field here poking through this area. So it's poking through. And maybe I'm going to move the magnet in and out, such as when I'm going to be close to the area, you have more field lines. And if I move away from it, you're going to have less field lines. Okay? Initially, the magnitude of the magnetic field is this. So that means B1 equals 0.05 T. So that will be the time elapsed. So delta T equals 0.1 second. And then the magnetic field is going to increase. So that means it will have more magnetic field lines. Okay? If you increase the magnetic field, that means you have more magnetic field lines. Okay, so now you have everything. Can you find the EMF? So you can talk to each other. Because you bring the magnet to work, okay, so you're going to have stronger magnetic field, and you move the magnet away, the magnetic field will be weaker. So you just apply this equation here. Okay, so it's just algebra. Don't stare, okay? If you stare, it doesn't really, I swear to you, it doesn't help. Do it. Right? You have to do it. EMF equals
That's nice. Well, I come to the same thing.
why is that I cannot erase anymore? I don't know why. Hmm.
18 is on the same.
What is this?
It's so different.
Yes. Good point. So you need to factor out. I would like to erase this, but it won't let me, so I don't know what to do. So EMF equals number of loops times B2, so 0. I need more space. I cannot. Oh, you know what I'm gonna do? No, I cannot even, it doesn't let me erase. I don't know why. Okay, I'm gonna write here then. I don't know why. So EMF equals 20. Okay, magnetic field 0.06 times the area A minus 0.05 the area, okay, divided by the time elapsed is 0.1. And the area is the same. So you can factor it out or you can just multiply. You can do the math. You can factor out the area if you want to do the math. But you don't have to, okay? You can just compute. You can factor out the area. Which one is 0.00? Yes. So the EMF equals 0.003 volt, right? So that will be 1, 2, 3. So 3 millivolt. Okay, do you agree? So what you have to understand is that when the magnetic field is stronger, that means more field lines. If it's weaker, that means less field lines poking through this area. Next time I will bring a unit, a video. So by the way, we're going to see that the quantity B times A, this is called, in physics, this is called the flux. And that's a way to find the number of field lines. But we'll talk about that on Thursday. Did you all get that equation, that value here?
Yes.